Good morning everyone and welcome to my presentation. My name is Jitendra Kumar. I am here to present my research work entitled Formal Analysis of Integer Multipliers by Building Binary Decision Diagram of Adder Trees. This research work was carried out under the supervision of Dr. Asutosh Srivastava and Professor Masahiro Fujita. I would like to start my presentation with the following statement. Can you perform the verification of a circuit against a specification or against a given circuit on a single platform when the circuit structure is completely unknown? In our research work, we tried to develop the similar kind of verification method. We are targeting multiplier circuits because these are the complex part to verify. My presentation will take around 16 minutes time. Since this is pre-recorded presentation, you are welcome to ask the questions in between. However, there will be a plenty of time for question answer in the end of the presentation. Let us start with the outline of the presentation. I am going to focus on the following major points. First, I will introduce about my project. Then I will brief the multiplier architecture, followed by general BDD construction of multiplier circuits and our BDD construction method. Further, I will explain the verification results. In the end of my presentation, I will show the advantages of my research work and the summary of my presentation. Moving to the next slide. Introduction. If you analyze the complexity of data path design circuitry, you will find that multipliers are the complex part of the circuit to verify. There are various multiplication algorithms available to generate the multiplier circuits. One can generate various multiplier architecture using the given link. These multipliers have many redundant gates and further can be optimized up to 20 to 40% in terms of number of EIG nodes. Now, verification of these optimized circuits are a challenge because after optimization, the architecture of multiplier circuits are changed. As we know, the complexity of BDD is exponential with the input size, hence it may not be feasible to apply general BDD construction method to verify integer multiplier circuits. So our goal is to reduce the complexity of BDDs for multiplier circuits and to verify optimized integer multiplier circuits. In our research work, we have used additional variable method to build VDDs for higher bit multiplier circuits and develop a method to check the equivalence between two multiplier circuits. Our proposed method can be directly applied to check the equivalence between two circuits. Moving to the next slide. Multiplier architecture. In this slide, I would like to brief the architecture of integer multiplier circuits before and after optimization. If you observe the multiplication algorithm, you will find that the multipliers can be divided into two phases. In first phase, partial product is generated, and in the second phase, these generated partial products are accumulated using various adder trees to generate final output. There are mainly two ways to generate the partial products. First one is simple partial product generator and second one is both partial product generator. In our study, we have focused on simple partial product generator method. However, a similar study can be done on both partial product generator. There are various adder tree architecture available to accumulate the partial products. For more detail, you can refer the website. Into a general multiplier circuit, the adder trees have multiple half adders and full adders and have clear boundaries and one can easily separate them. But After optimization, the boundaries of adder trees are destroyed, and there may be a possibility of direct connection of primary input to the second stage, as shown by the red lines in the figure. The extra lines are added due to the don't care utilization in optimization, and hence the separation of different blocks become difficult. In the upcoming slide, we will see why these red lines are creating problems to, to apply the VDD based verification method. Moving to the next slide. BDD construction. In this slide, we will see the general BDD construction and BDD construction using additional variable methods. Table 1 shows the general BDD construction results for integer multiplier circuits. From this table, it is clear that the BDDs can be constructed up to 18-bit multiplier circuits only using general BDD construction method, where primary inputs are used as BDD variables. Also, the number of BDD nodes varying exponentially with the input size. And beyond 18-bit multiplier circuits, a node overflow problem occurs. So it may not be feasible to apply BDD directly to verify integer multiplier circuits. However, if we use additional variable methods, then the complexity is limited to the fourth order of the input size. This method was originally proposed by J.R. Burch, and very limited study has been done on this method so far. In this paper, we will use additional variable method to construct BDDs for higher bit multiplier circuits. We are using pre-computed partial products as BDD variables, such as the partial product x0 y0 become x00 y00, x0 y1 become x01 y10, and so on. For each occurrence of input is represented as unique variable. However, these representations are considered as same while generating counterexamples. For a n cross n bit multiplier circuit, there are total n square partial products, and to calculate each partial products, two inputs are required. Hence, total 2n square variables are generated and considered as primary input to generate BDDs. Using pre-computed partial products, the problem of multiplier verification is converted into the problem of adder tree verification. In the next slide, we will see the VDD construction results using this method and the computation complexity of this method. Moving to the next slide. Continuing the VDD construction, we applied additional variable method to generate VDDs for array multiplier circuits. Table 2 shows the VDD construction results for array integer multiplier circuits. To construct the VDDs in the first experiment, we fixed the variable order as low to high, and in the second experiment, we fixed the variable order as high to low. In the given results, we can see with the high to low variable ordering, our method were able to construct BDDs up to 80 bits, and using low to high variable ordering, our method were able to construct BDDs up to 120-bit multiplier circuits. The interesting point to note here is the complexity of BDD nodes remains third order with high to low variable ordering and fourth order with low to high variable ordering, with the increase in the input size of circuit. In the case of high to low variable, a precise third order formula can be derived as 4x cubed minus 6x square minus 4x plus 13. The BDD package is available online and you can find it on the given link. Moving to the next slide. In this slide, we will see the verification of general multiplier circuits. The BDD generation results presented in table 2 shown in the previous slide can be taken as the reference model, and we can verify general multiplier circuits by constructing BDDs and comparing the general BDD nodes with the reference model. As we know that the BDDs are canonical for a given function and for a given variable ordering, hence two circuits for same function should have isomorphic BDDs and the number of nodes in the both generated BDDs will be equal. We constructed BDDs for various architecture of adder trees up to 40 bits. You can see table 2 and table 3 that the number of BDD nodes are equal for the same bit of multipliers. Hence, we can conclude that the circuits are equivalent to the reference circuit by just checking the number of generated BDD nodes. Further, you can see that the BDD generation time is varying for the different architecture for same size of circuit. This is due to the intermediate gate selection order. We can accelerate the algorithm of BDD generation by using a good intermediate gate selection order. Moving to the next slide. Continuing the verification. So far we have seen general multiplier verification by comparing the BDD nodes with the golden model. In this slide, I would like to demonstrate the verification of optimized multiplier circuits by equivalence checking between two multipliers. As I have already discussed that the optimization introduces a few extra lines parallel to the partial product generator. Here we cannot directly apply additional variable method to construct BDDs of optimized multiplier circuits because the extra line can change the functionality of adder trees. However, these lines do not alter the overall functionality. Since we are constructing the BDDs only for adder trees phase, hence the BDDs for two equivalent circuits may differ due to these parallel lines. To overcome this problem, we proposed a case split method where for each extra signal lines we are considering two cases. First, fixing the values of signal lines as 0, and in the second case we are fixing the value of signal line as 1. We are doing the similar modification in the reference circuit also. Further, we are constructing BDDs for each cases and then generating miter BDD by performing XOR operation between two BDDs. The first BDD in the miter circuit is the BDD of reference circuit and the second BDD is the BDD of circuit under verification. Now we are trying to generate counterexamples which are not in the don't care set. With this method, we verified optimized circuit up to 32 bits. The results are shown in table 4. We compared our results with algebraic backward rewriting method. You can see the verification results of algebraic backward rewriting method where most of the time these methods were not able to complete the verification within given time limit, which is 2000 seconds. The algebraic backward rewriting methods depend upon the multiplier architecture. As you can see, for the same 16-bit multiplier circuit, verification did not completed. In our case, it is working independently with the circuit structure and we were able to verify a wide variety of structure. Moving to the next slide. I would like to brief the advantages of equivalence checking using BDDs. This method can give foolproof guarantee and we can easily cover corner cases. This method can work independently with the multiplier architecture and can verify a wide variety of multiplier circuit structure. We can easily generate counter example to detect bug and to localize the bug. Moving to the next slide. So that brings to the end of my presentation. Now I would like to summarize my presentation. We first discussed the change in multiplier circuit architecture after optimization. Then we discussed the BDD construction of higher bit multiplier circuits, followed by the method of equivalence checking between two multiplier circuits using BDDs. Finally, we presented the verification results of optimized multiplier circuits. Thank you very much for your kind attention. If you have any questions, I would like to take an opportunity to answer them, and if you have any suggestions, please let me know. This is pre-recorded presentation. If you have any questions left unanswered, then please send me on the given email ID. I will try to answer them as soon as possible.